Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on 3-phase 3-wire AC systems. By solving these problems, we shall learn how to determine the line currents, the load voltages, the load impedances or the neutral shift voltage when a symmetrical 3-phase 3-wire AC system supplies power to a star-connected unbalanced 3-phase load. An unbalanced star-connected load is supplied from a balanced 3-watt system. The current taken by one branch is 20 ampere at a power factor 0.8 lagging. The current taken by the second branch is 10 ampere at a power factor 0.75 lagging. We have to determine the current in the third branch and its power factor. Let us first write down the given data. Magnitude of current flowing through the A phase IA equals to 20 ampere and load power factor cos phi A equals to 0.8 lagging. Let us now calculate power factor angle. Phi A equals to cos inverse 0.8, that is equal to 36.8699 degree. For a balanced 3-watt system with phase sequence ABC, taking phase voltage VA as reference, we can write phase voltage VA equals to V phase at an angle 0 degree, VB equals to V phase at an angle minus 120 degree and VC equals to V phase at an angle plus 120 degree. Here phase current IA lags phase voltage VA by an angle phi A. Therefore, in complex form, phase current IA equals to IA at an angle minus phi A, that is equal to 20 ampere at an angle minus 36.8699 degree. In Cartesian form, this may be written as 16 minus j times 12 ampere. Given magnitude of current flowing through the B phase IB equals to 10 ampere and load power factor cos phi B equals to 0.75 lagging. Now we shall calculate power factor angle. Phi B equals to cos inverse 0.75. That gives us 41.4096 degree. Here phase current IB lags phase voltage VB by an angle phi B. Therefore, in complex form, phase current IB equals to IB at an angle minus 120 degree minus phi B, that is equal to 10 ampere at an angle minus 161.4096 degree. In Cartesian form, this may be expressed as minus 9.4782 minus j times 3.188 ampere. In Cartesian form, we have obtained current flowing through the A phase IA equals to 16 minus j times 12 ampere and current flowing through the B phase IB equals to minus 9.4782 minus j times 3.188 ampere. Let the magnitude of current flowing through the C phase be IC. Applying Kirchhoff's current law to node N dash, we get IA plus IB plus IC equals to 0 or IC equals to minus of IA plus IB. Using values, we get minus 6.5218 plus j times 15.188 ampere. This may be written in polar form as 16.53 ampere at an angle plus 113.24 degree. Therefore, magnitude of current IC equals to 16.53 ampere, and current flowing through the C phase leads the reference by an angle 113.24 degree. Angle between VC and IC, phi C equals to 120 degree minus 113.24 degree, that gives us 6.76 degree. Let us now calculate load power factor. Cos phi C equals to cos of 6.76 degree, that gives us 0.993 lagging. A three-phase three-wire load is star connected. The phase voltage of 2 amps are Vrn dash equals to 100 volt at an angle minus 10 degree and Vyn dash equals to 150 volt at an angle plus 100 degree. We have to determine voltage between the star point of the load and the supply neutral. Let us first write down the given data. Voltage drops across load impedances Vrn dash equals to 100 volts at an angle minus 10 degree. This may be written in Cartesian form as 98.4808 minus J times 17.3648 volt, and Vyn dash equals to 150 volts at an angle plus 100 degree. In Cartesian form, this may be written as minus 26.0472 plus J times 147.7212 volt. Expression for line voltage Vry equals to Vrn dash minus Vyn dash. Using values we get 124.528 minus J times 165.086 volt. In polar form, this may be written as 206.7864 volt at an angle minus 52.972 degree. Line voltage Vry may be expressed as VL at an angle minus phi Ry. Therefore, magnitude of line-to-line supply voltage VL equals to 206.7864 volt, and phase angle of this line voltage phi Ry equals to 52.972 degree. For a three-phase three-wire star-connected load, supply voltage per phase V phase equals to VL by root 3, that is equal to 206.7864 divided by root 3, that gives us 119.3882 volt. Here load voltage Vyn dash leads load voltage Vrn dash. Therefore, we can assume phase sequence RBY. In this case, phase voltage Vr leads line voltage Vry by an angle 30 degree. Therefore, phase voltage Vr equals to V phase at an angle 30 degree minus phi Ry, that is equal to 119.3882 volt at an angle minus 22.972 degree. In Cartesian form, this may be expressed as 109.9202 minus J times 46.595 volt. Now we shall calculate voltage between the star point of the load and the supply neutral. Vn dash n equals to Vr minus Vrn dash. Using values we get 11.4394 minus J times 29.2302 volt. In polar form, this may be written as 31.3889 volt at an angle minus 68.6268 degree. In the circuit shown, line currents are IA equals to 1.94 ampere at an angle minus 0.737 degree, IB equals to 4 ampere at an angle minus 117.7 degree, and IC equals to 3.57 ampere at an angle 91.4 degree. We have to determine voltages across each phase of the load and voltage between the neutral of the load and the neutral of the generator when phase voltage is 120 volt and the phase sequence is ABC. We have to take A phase voltage as reference. Let us first write down the given data. Current flowing through the A line, IA equals to 1.94 ampere at an angle minus 0.737 degree. Current flowing through the B line, IB equals to 4 ampere at an angle minus 117.7 degree, and current flowing through the C line, IC equals to 3.57 ampere at an angle 91.4 degree. Taking A phase voltage as reference, we can write VAN equals to 120 volts at an angle 0 degree. Per phase load impedances ZA equals to R, that is equal to 18 ohm. This may be written in polar form as 18 ohm at an angle 0 degree. ZB equals to RC minus J times XC, that is equal to 40 minus J times 20 ohm. This may be written in polar form as 44.72 ohm at an angle minus 26.565 degree, and ZC equals to RL plus J times XL, that is equal to 30 plus J times 40 ohm. This may be written in polar form as 50 ohm at an angle 53.13 degree. Let us now calculate voltage drop across each load impedance. VAN dash equals to IA into ZA. Using values we get 1.94 at an angle minus 0.737 degree into 18 at an angle 0 degree, that gives us 34.92 volt at an angle minus 0.737 degree. VBN dash equals to IB into ZB. Using values we get 4 at an angle minus 117.7 degree into 44.72 at an angle minus 26.565 degree, that gives us 178.88 volt at an angle minus 144.265 degree, and VCN dash equals to IC into ZC. Using values we get 3.57 at an angle 91.4 degree into 50 at an angle 53.13 degree, that gives us 178.5 volt at an angle plus 144.53 degree. Expression for voltage between the neutral of the load and the neutral of the generator, Vn dash n equals to Vn dash minus Van. In Cartesian form, Van may be expressed as 120 plus J times 0 volt, and Van dash may be expressed as 34.9171 minus J times 0.4492 volt. Using values we get Vn dash n equals to minus 85.0829 minus J times 0.4492 volt. In polar form, this may be written as 85.084 volt at an angle minus 179.7 degree. Three impedances ZR, ZY and ZB are connected in star across a 440 volt three-phase symmetrical supply. If the voltage of load start point relative to supply neutral is 200 volt at an angle 150 degree and Y and B line currents are 10 ampere at an angle minus 90 degree and 20 ampere at an angle 90 degree respectively, all with respect to R phase supply voltage, we have to determine the values of ZR, ZY and ZB when phase sequence is RYB. Let us first write down the given data. Line to line supply voltage VL equals to 440 volts. For a symmetrical three-phase supply voltage per phase V phase equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. Taking R phase voltage VR as reference, for phase sequence RYB we can write phase voltage VR equals to V phase at an angle 0 degree, that is equal to 254 volts at an angle 0 degree. This may be written in Cartesian form as 254 plus J times 0 volt. Vy equals to V phase at an angle minus 120 degree, that is equal to 254 volts at an angle minus 120 degree. This may be written in Cartesian form as minus 127 minus J times 220 volts, and Vb equals to V phase at an angle plus 120 degree, that is equal to 254 volts at an angle plus 120 degree. This may be written in Cartesian form as minus 127 plus J times 220 volts. Given neutral displacement voltage Vn dash n equals to 200 volts at an angle 150 degree. This may be written in Cartesian form as minus 173.2 plus J times 100 volt. Now we shall calculate voltage drop across each load impedance. Vrn dash equals to Vr minus Vn dash n. Using values we get 427.2 minus J times 100 volt. This may be written in polar form as 438.75 volt at an angle minus 13.175 degree. Vyn dash equals to Vy minus Vn dash n. Using values we get 46.2 minus J times 320 volts. In polar form, this may be written as 323.32 volt at an angle minus 81.785 degree, and Vbn dash equals to Vb minus Vn dash n. Using values we get 46.2 plus J times 120 volts. This may be written in polar form as 128.586 volt at an angle plus 68.943 degree. Given current flowing through the Y line, Iy equals to 10 ampere at an angle minus 90 degree, this may be expressed in Cartesian form as 0 minus J times 10 ampere, and current flowing through the B line, Ib equals to 20 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 20 ampere. Let the current flowing through the R line be IR. Applying Kirchhoff's current law to node N dash, we get IR plus IY plus IB equals to 0. Therefore, IR equals to minus of IY plus IB. Using values, we get 0 minus J times 10 ampere. This may be written in polar form as 10 ampere at an angle minus 90 degree. We have determined voltage drop across each load impedance Vrn dash equals to 438.75 volt at an angle minus 13.175 degree. Vyn dash equals to 323.32 volt at an angle minus 81.785 degree, and Vbn dash equals to 128.586 volt at an angle plus 68.943 degree. Now we shall calculate per phase load impedances. ZR equals to Vrn dash divided by IR. Using values, we get 438.75 at an angle minus 13.175 degree divided by 10 at an angle minus 90 degree. That gives us 43.875 ohm at an angle 76.825 degree. This may be written in Cartesian form as 10 plus J times 42.72 ohm. Zy equals to Vyn dash divided by Iy. Using values, we get 323.32 at an angle minus 81.785 degree divided by 10 at an angle minus 90 degree. That gives us 32.332 ohm at an angle 8.215 degree. This may be written in Cartesian form as 32 plus J times 4.62 ohm, and Zb equals to Vbn dash divided by Ib. Using values, we get 128.586 at an angle plus 68.943 degree divided by 20 at an angle 90 degree. That gives us 6.4293 ohm at an angle minus 21.057 degree. This may be written in Cartesian form as 6 minus J times 2.31 ohm. So today we have solved a couple of numerical problems on three-phase 3-wire AC systems. By solving these problems, we have learned how to determine the line currents, the load voltages, the neutral shift voltage or the load impedances when a symmetrical three-phase 3-wire system supplies power to a star-connected unbalanced load. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.